Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce Asiya Mahboubi, who will talk about formal proof-producing decision procedures. And Asiya is visiting us from the Bay Area, where she's staying currently, and otherwise, permanently, she's at INRIA in Paris. Thank you.
Thank you. Thank you very much for inviting me. I'm mainly working with a piece of software called Interactive Formal Proof Assistance. So there are three features in that software. They are proof assistants. So it means that they can help you check your proof, or more likely have your proof checked by a machine. That's when you're not confident in human referees. They are interactive and not automated. So it means that you will require some input from the user and not trust a push-button decision procedure. And most importantly, they are formal. So it means that you require the highest possible guarantee of correctness, which is, and the interactive part is the price to pay for that. So this is usually the architecture of such a software. So you have different parts in the engineering of such proof assistant, and different choices that are possible at each level. So first, you have to choose your formal language, means the underlying logic. That will be your language for describing the statements you have to prove and also the proofs that you build. Then you will have the proof engine, so it's the part of the software that help you building the actual proofs. And of course, the formal language gives a very, very low-level language for the description of some proofs. So you will probably not be able to describe your proof yourself using this language, like you would not program very complicated algorithm directly in assembly code. But the proof engine will help you with some automation and any feature you like, and maybe non-correct ones, since you will probably require your proof checker to be a separated piece of software. So if these proof engine and proof checker are really separated, you can have your proof engine as faulty as you want, because you have a very careful checker that is completely distinct and that will check after the possible error made by your proof engine. Okay, then you're already done, but you're done with the software part, and you're not done with the software engineering part. And you will probably have to choose carefully the language, the input language you will use on top of these formal language and proof engine, because for different pieces of formalization, probably different strategies will be efficient for that. And also, you will probably have a hard time trying to combine your various formalization into a very complicated one. And that's what we usually call formal software engineering. Anyway, so what I will be talking about today is mainly located at the proof engine part. And it's about developing decision procedures that help you automate some part of the formal language. So first, let's give some example of proof assistance. So the scheme I gave was very, very general, but of course, there's a huge family a huge family of proof assistants, and you can have as many different flavors as you can find in programming language. So you can have very lightweight ones or large ones, very heavy. You can have a very much an important distinction between the proof checker and the proof engine, or not quite a distinction, like it's the case for the PVS system. You can have powerful automation available, or not that quite powerful automation available. You can have the notion of proof object, that is something built by your proof engine and saved when it's checked. Or you can simply forget the proof and only check the statement and then store it somewhere. And of course, you can choose the flavor of logic you'd like, and you have lots of choice for the set theory, type theory, different kind of type theory. And there are other possibilities I want.
So you say, Coq generates recheck of the proof objects, but it also has a, doesn't it have an LCF core?
It's not exactly an LCF core. So it comes from the LCF family, but it's not exactly an LCF
Because
style.
what the whole family does is, instead of a proof object, you have a tactic.
So it stores, so the HL family once saved the proof tree generated, but the Coq proof objects are the lambda terms that you build. So these lambda terms are recheckable. And that's what you store. You don't have this notion of a type for theorem and then everything in this type is a correct proof. That's what is the principle of LCF style proof assistant. In Coq, you can maybe define some terms that are not well typed, but the checker won't accept them.
Yeah, but my question was, so you say there's no proof object in the whole family?
For the moment, for the present implementation of the whole family, they no more have recheckable files that you can distribute and have checked by other implementation of the checker.
Okay, in that sense.
And that's why in the Coq framework, you can consider having proof sharing, for instance. You can consider re-implementing a kernel for Coq, and that's something that has been done. And then you take some proofs that have been developed by the first version of Coq and check them with the other one. Okay?
You could, in principle, save the LCF
yes, that's true.
In all tools, just that they don't.
Yeah, because it's huge, in fact. So that's not a feature they want to support, and in Coq, it's something that people want to push and consider important, so they are trying to optimize the way the proof objects are produced and stored and so on. I don't say it's a good idea or not, it's just different concerns. Okay, so this kind of software have a life of their own, so there are really grand projects that are entirely devoted to some formalization of large scale. I'm listing a very arbitrary small number of them here. And you'll see that 3 of them are in my favorite system, which is the Coq system. So the first one was the four-color theorem, which was proved by Georges Gontier at Microsoft Research Cambridge, and Benjamin Werner, who is the leader of the team I'm working in at INRIA. You can also consider the Mizar library. So Mizar is a set theoretic proof assistant. As a very, very large formalization project, it's probably the largest body of formalized mathematics available in any system. So Xavier Leroy and others have proved the correctness of a C compiler using, again, the Coq system. There are also much lower level pieces of software that have been verified, just like operating systems. So I think that project is still ongoing research, but they already have impressive results. Then maybe one of the largest project that is currently led is the formal proof of the Caprica conjecture. So it's a mathematical theorem about sphere packing, saying that the densest sphere packing you can obtain is the one that your greengrocer uses. And this conjecture has been proved in the 90s by Thomas Hales, a mathematician at Pittsburgh. And so since his proof involves a large body of computation made by special programs he wrote himself, referees were not able to really agree with his proof and put a disclaimer at the beginning of the publication. So he launched this grand effort to formalize the whole proof. And this is a very interesting one because effort is spread among different systems. So at the end, there will be a problem with gathering everything. And finally, this is a project I'm involved in, and it's about formalizing a large theorem of group theory in the Coq system. It's a project which is done in the INRIA Microsoft Research Joint Center in Paris, in a team led by Georges Gontier again. So, what about decision procedure then in this context? So, as I said, the logic that you're choosing, any logic you would be choosing to serve as a basis, as foundation for your proof assistant, is probably really too low level language for, let's say, formalize your group theory theorem. So you will probably need some automation to help you developing these proofs. And not only for this low level reason, but also because usually this kind of let's say, linear problems, for instance, if you have a set of linear constraints and one lemma of your proof is to prove that it's not consistent, then it's really an uninteresting part of your proof. So you don't want to prove it by hand. And that's why you will probably ask your developers to provide you with automated decision procedures, just like decision procedures that are available outside the context of proof assistance. But here, it will probably be a little more tricky to implement them. First, because you will have not only to provide an answer to your problem, but also a formal proof of this answer. And also because the user of a proof assistant will probably require that this decision procedure has a really precise scope. And he will probably ask to know exactly when the decision procedure is supposed to fail, because otherwise the robustness of the script he's developed will not be that robust. Okay, so as I already said, my favorite system is the Coq proof assistant, developed at INRIA since the 80s. It belongs to the type theory-based systems, and this in particular means it relies on the Curry-Howard principle. So this simply means that the theorem you want to prove is defined as a type, just like in functional programming languages. So once you declare this type, if you claim that you can prove the theorem, it means that you are able to build a lambda term which is correctly typed by this type, corresponding to the statement. So the proof checker is only a type checker for this lambda calculus. And the proof engine is something that helps you building complicated lambda terms. So it really means that you can separate the proof checker from the engine that helps you building the lambda term. And this is why Coq is supposed to verify this Poincaré principle, this principle of separating development and checking.
Incidental question: is this the same Poincaré as the Poincaré conjecture, the famous one?
Yeah.
He was talking about code for proofs and proofs.
Yeah. So he wrote some essays about science, and so in these essays he was talking about the science and how science should be written and how science should be checked. So it was really before even before the revolution that led to Gödel and Hilbert thoughts. But it's the precise book is called Science and Hypothesis, if you're interested. Okay, so I'm not trying to convince you to use the proof assistant, but the nice feature I find in this system is that you can really consider it as a pure functional programming language. So it's the lambda calculus that is underlying the proof assistant. And recently, this feature of programming language have been enhanced by a compiler and also by improvement of the arithmetic that you can use. Apart from that, there is also a program extraction mechanism, which means that you can translate your constructive proofs or even your programs you write in Coq to functional language like OCaml or Haskell. And also developing your proofs using the Coq proof assistant can be fun because apart from the automation you can get from decision procedures, you can also use the powerful type system and especially its higher order feature to have some automation like proof style type classes helps you developing and inferring proofs. But of course there are also some not so nice features like in the fact that automation is rather low compared to other systems like Isabelle or HOL. And it's the same as in many other systems that reusing libraries is really hard. And probably when you develop a library, you will probably be the only user of it most of the time. So what is like developing proof-producing decision procedure in that context? So in the context of a proof assistant that can also compute, that can also be used as a programming language. So the idea is that you have a problem, and this problem means you want to decide a property on a certain object, small t, which is typed by capital T. Okay? So there are many ways of considering this problem. The first one is called the autarkic approach, meaning that you will not rely on anything else than your own resources inside Coq. So what does it mean? It means that you will use Coq really like a programming language to program the decision procedure really using Coq, and this will lead to a f, this decision procedure, which you can consider as a function from type t to bool, let's say. Then you will prove the correctness of this procedure, so it means that you will provide a formal proof of the correctness of the algorithm you use to program f. And this is this proof here, this theorem, meaning that, so you only prove that it's correct and not sound, of course. So you prove that if the answer is true, then you really have solved your problem and you have built a formal proof of P of t. Okay? Then each time you will have a goal which is of this shape, you will apply this lemma, then compute the value of f of t, and you will be done. So this has the advantage of leading to very short proofs because it's only applying this theorem and performing this computation. But on the other hand, it might require a lot of effort because this can be very hard. That's why not all decision procedures in Coq are done this way. And there's another one called the skeptic approach, which is to use external resources. So this time, you will program or have programmed the decision procedure you're interested in any arbitrary context. So any other language, any other setting. The only thing you require is that this external, once again, decision procedure provides some trace or certificate and not only a yes or no output. So again, if you are interested in solving problems of the form P of t, suppose that you also have a notion of certificate which gives for any instance small t a certain object. And you also have a certificate checker which is able to, from a certificate, compute an answer. And what you want is that if the checker answers true on a certain certificate, and this certificate is associated to entry small t, then you have proved P of t. Okay? So this is really something that we want to push because, of course, if the notion of certificate is well suited, then the effort of formalization is much smaller, and also the efficiency of outside external decision procedure can be a lot more powerful than inside programs in the Coq system. So it's an interesting approach but it's not adapted to any decision procedure or any theory. So it basically requires two things. First, that the theory accepts a notion of certificate, and a good one, because if it's a lot of effort to prove the correctness of the checker, then it's probably not a good solution. You will also have to check efficiently your certificate, meaning that maybe evaluating the value of the proof checker is something you want to perform efficiently, and possibly this involves computations, maybe with large numbers. And from the outside world, you want also, of course, an efficient decision procedure, but also one that gives you a certificate. So, so this interest we have in certificates and certificate checking is not new, but it has been recently renewed by the growing interest of the SMT systems for traces and outputs, traces of outputs. So if we can efficiently take benefit of that SMT outputs, then we will probably be able to incorporate part of the powerful decision procedure developed by this community inside the proof assistant. Okay, so of course, this is something that is interesting for the proof assistant community, but it's probably also something that will have a benefit for the SMT tools as well, because since critical code developers are often interested in verification and critical verification of their programs, they will be happy to be able to have a formal guarantee that the result of the decision procedure they are using is correct. So I think that this need for decision procedure producing the certificate is something that is shared among several kind of users of these decision procedures. Okay, so this is a small summary of what, up to my knowledge, are the experiments that are led concerning the integration of proof assistance with SMT tools. So I know that the whole light system has been linked with the CVC light system for linear real arithmetic, but the report was not so positive on it, and I really don't know why. Probably the most successful effort was the integration of set 3 with the Isabelle Hall system, which was done by...
Thanks for pointing it out.
Sorry? I didn't...
Thank you for
But that's true. I mean, I wish we could do... I could have said is the integration of coq with, but it's not the case. So this...
so this here is your...
Yeah, so this is a French project, so it's founded by the French Research Agency, yes. And so we're a consortium working on that.
It's a consortium, yeah.
So it involves people from INRIA, people from 2 other universities, and also some people from the B method. So, so it means, okay.
Most complete?
Yeah, so it's the most advanced project, so they can really check complete traces. So in the context of...
There's a missing bullet.
There is a missing bullet?
We're doing some of this stuff as well.
Oh, sorry. I would be happy to hear about it. I said up to my knowledge, and I put a question mark. So. So this is really preliminary for the moment. So since the foundations of Isabelle, for instance, and coq are really different, the issues of importing such traces of large problems like the ones that are described in the SMTlib are not the same. And so, for instance, people have worked hard to integrate SAT traces and into coq. That was really a difficult problem, whereas in Isabelle Hall, they know how to do that they have known this for a long time. So the idea is that since Coq has computational skills that this system doesn't have, we hope that there will be different targets that will be dealt by the Coq approach and not by Isabelle Hall 1.
So did this Sophia Antipolis?
Yeah, that's the Daxful talk.
Okay.
So they are also part of this consortium. Yeah. Okay, so for up to now, I have only been very general on proof assistant and decision procedures. So something that is of particular interest for me is the decision procedures that are working with real numbers. And this is the kind of problem that you're facing when you have lemmas or problems that come from real arithmetic. This can happen if you're facing combinatoric problem or a hybrid system or control problem, things like that. Or if you're only developing a formal proof of, I don't know, number theory, maybe. And some lemmas are of this shape. And you don't want to prove them by hand because it's just boring. So this shape is you can have equality constraints, order constraints, strict or large, on polynomials with, well, I put on R here, but it's more rational coefficients. You want them to be exact computations and not floating point, for instance. And of course, variables here are quantified over real numbers. Okay, so this is the syntactic description of the problems, but it's of course too coarse-grained, and many different sub-families of problems can be distinguished here. And the first one, of course, is the one of linear problems. So it means that all the polynomials involved here are linear. You don't have product of variables. So geometrically, this means that each constraint here, like inequality constraints, corresponds to half planes. Okay, and each equality constraints correspond to just a face of this kind of polytope, a plane. So what you want is to see if the intersection of half planes and planes is empty or not. That's just what this kind of problem describes. So here there is a polytope, and probably you will find somewhere the solution you're looking for. Okay? So it's a well-studied problem, and solutions have, the algorithm for solving this kind of problem has been known for really long, like 2 centuries. And we know efficient ways of looking for such solutions, like simplex-based one or interior point. So it's really something that is really important, but well studied. And it's not only the case that we can decide what is the solution, it's also the case that we can have a good notion of certificate for that kind of problems. So there is a very famous property of this linear programming area, which is called duality. And this is the Farkas lemma, saying that basically when you know how to solve a problem, you also know how to certify that a problem has no solution. So of course, if a problem has a solution, an easy certificate is a candidate solution, and it's easy to check that it's actually satisfying the initial constraint. But also, if you have a negative answer, so this means this linear problem has no solution. Well, there's a linear problem that has a solution if and only if this was infeasible. So that's a certificate. If you have a solution for this, then it's a certificate for the infeasibility of the first one. Okay, so this is just a remark that using the Farkas lemma, you obtain your certificate by a second run of your decision procedure, but you're not forced to. So if you use a simplex-based decision procedure, so you know the simplex is optimizing a linear function under linear constraints. So if you're a linear function is constant. You only test that the feasible region is empty or not. And so this is used as an algorithm in some SMT tools for deciding linear arithmetic. And this kind of algorithm gives you a certificate for free, even if it answers unsat. Why so? Because, in fact, the unsat answer is obtained by obtaining this. So suppose you start with these 3 constraints. In fact, if the simplex algorithm answers no, it means that it has found some coefficients that will give you an impossible inequality. So here you have this system. It's obviously unsat. But if you make the sum of the 2 last, you see that if the 3 initial constraints are valid, you should have 0 smaller than -2. Okay? So that's it for the linear problems, but the real challenge for me is the nonlinear problems. So the nonlinear problems is the generic form of the initial description I gave. So now all the polynomial involved here can be of any degree and any shape you'd like. And you want to know whether this is satisfiable or unsatisfiable. Like once again, if you find a SAT certificate, it means that you have a solution and it's easy to check. But what is a good certificate for unsat problems of this shape? So the idea is that it's much more difficult than the linear case, because the geometry involved is really more complicated. So remember that when we were dealing with linear problems, we were only building polytopes. Now you can have this kind of shape. So if I remember correctly, this is a problem of degree 7. This should be 9 and 11. It's not that much. And it's 3 variable each time, because we are in the 3-dimensional space. So we can really have very complicated problems that are not syntactically very complicated. So it's really difficult to find out that a given problem is hard to solve. So, well, even if it's complicated, still it's decidable in theory. So the full first-order theory of real arithmetic with order is decidable and is known since Tarski. So it was published in the late 40s, but he came up with the result like in the 30s, I guess. So, well, it's much later than for the linear case. Also, this was a logical result for like 40 years. And it was understood geometrically and considered as a geometrical tool much later, like in the 80s. Till the 80s, well, till the late 70s, the decision procedures that were known were in complexity a tower of exponentials. So it was not really an efficient tool. But then Collins came up with the so-called cylindrical algebraic decomposition, which was only doubly exponential in the number of variables. And even if it's horrible, this was still implementable and started being used as a decision tool. So again, well, it's bad, but for the moment, I know no other algorithm that can be implemented. And it's very, very difficult to split cases against some efficient heuristic that would apply to special shapes, because there are not really syntactic criterion to decide if it's a good candidate for such a method or another. We'll see that it's not that true, but usually it's difficult. So most of the mathematics that are involved in the decision procedures we know for real arithmetic is described in this book, which is a comprehensive reference. So now I will explain in 3 slides what is this decision algorithm that is able to decide the full first-order theory. So we start with a family of polynomials, and in fact, what we will come up with is a partition of the space. So just imagine you have 3 variables, so you have a problem in the 3-dimensional space. So you will partition R3 into cells over which the family of polynomials have constant sign. And then you will just look for the condition you want by browsing this finite state space. Okay? So if you have a problem with only one variable, then it's a so-called root isolation problem. So suppose that you have only one polynomial. There's an undergrad formula saying that you can bound the roots, and then you can, by a dichotomy process, isolate the root of the polynomials. Then repeating this process, you can do the same for every root of every polynomial in your initial family. And then, well, using this dichotomy process and possible GCD computations, you will come up with a list of intervals, and you will know the sign of each polynomial on each interval. So this dichotomy process with GCD computations is called the Uspansky method, and the dichotomy process is efficient when you use Bernstein polynomials. That are the keywords. Then, if you have a problem in higher dimension, you will use projection. You will basically...
Question from...
Sorry.
Yeah, we could actually understand this if you went a little slower, I think. You want trying to finish?
I'm trying to finish within 5 minutes. But I'm happy to answer.
5 minutes? All right, well, let's finish in 5 minutes, and we can come back.
Right. Finish in 10. Finish in 10, 15 minutes.
Would you like me to comment on the last slide?
No, you just go as you like, and then we'll come back.
Okay. So then if I have a problem with more than one dimension, I will solve it by recursion on the number of variables. So all the trick is to define a clever projection operator, which will make my problem with n plus 1 variable a problem with n variables. So suppose that I recursively know how to compute my cylindrical decomposition for the n variable problem. Then, since it's not only a partition but a cylindrical algebraic partition, it means that from this information and from a set of sample points of this decomposition, I know how to solve my initial problem. Okay, because well, maybe an example will be, yeah.
This recursive decomposition, is it also giving you a quantified elimination
Sure.
procedure? But the original decision problem you propose is just existential.
No, so yeah, the original...
The satisfiability problem.
Yes.
You're asking existential.
Yes.
And you're applying a general quantified elimination
Yes.
procedure for it. Are there any steps that are more than you really need for the existential case?
Yeah, so I will comment on that a bit later if you... So the idea is that for unsat existential problem, it's not easy to find a more efficient way of certifying than computing this kind of objects.
When they're unsat.
So if I don't have a solution for my initial problem,
Yeah.
then how do I certify it? So
Okay.
I will maybe answer that later. So, but I agree with you that for the moment I am interested in an algorithm that will be complete for the complete first order theory. Mm-hmm. So once again, it's a recursive algorithm. So you start with a family with n variable, you project it, you have a solution for the problem with one variable less. So this means that you have this partition. And since you know how to deal with the one variable case, on each cell of this partition, you will have a new one variable problem, and solving this one variable problem will give you the appropriate decomposition for the initial family. So this is the kind of decomposition you obtain. So I have here drawn the cylindrical decomposition that is computed for the family reduced to a single polynomial, which is x2 plus y2 plus z2 minus 1, which is the sphere. So you project it, and the family in two variables you obtain have roots on this circle. But you don't know it yet. In fact, you're in the projection phase. So you project it once, eliminating z. Then you project it a second time, eliminating y. And you have a one-variable problem, which probably has polynomials that have only two roots here. And then you are in the lifting phase. So here you have 5 cells. One here, one at this root, one at this open interval, again one root, and the half line here. So you choose one sample point by cell. And what is remarkable is that above each cell, the behavior of the family in two variables is uniform. So here you will never meet the roots. Here is an exceptional point. Here, any point in this interval, if you draw the line above it, will cross the roots 2 times. And this is the symmetric here. So this lifting phase for the phase from one variable to two variable will give you these cells. So a half plane, 2 lines, and here you have 1, 2, 3, 4, 5 cells. And you do the same again. So you choose one point in each cell here, and you lift the problem. You study it on the fiber above the point. And at the end, you have this decomposition, which is very, very much complicated, because at the end, you come up with a number of cells, whereas if you look at the initial problem, the sphere determines only 3 components in the cell. The outside of the sphere, and there the polynomial is positive. The sphere itself, and it's 0 on the sphere. And inside the cell, it's negative. So you only have 3 cells. But the decomposition here, since it's cylindrical, give a combinatoric explosion that you cannot avoid. Okay. So why do you come up with a decision procedure for first order? So here is a very simple example with 2 polynomials, and you want to prove that there exists x, there exists y, such that these constraints are satisfied. So this is the set of roots for each polynomial. So you project it. This will be the roots of the one variable family. You lift, you compute the sign of each cell on each cell, and this is the result of the sign computation. So what are you looking for? You're looking for 0 and 0, and this is here. Okay? Sorry?
So after a lot of dots, you correct to 0.
Yeah. So, but when I made my cylindrical algebraic computation, I didn't know I had a purely existential problem. So if I have a for all somewhere, then maybe I have to compute more than just a witness. So in fact, the result here is a tree. So you will have here a description of 5 cells for the x cells. So you have an open interval here, a point here, an interval here, a point here, and again a half line here. And above each cell, you will determine how many sign conditions you can fulfill. Here, 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 here. So if you have a for all x, exist y quantification, you will look for under any point of the x level if there exists a child for the y such that your sign condition is fulfilled. So here you have the sign condition.
So what you're also describing is how it gets used in the quantified elimination procedure.
Yeah.
You bring it into pre-next.
The structure of the cylindrical decomposition is exactly this one. So it's the output.
Bring it into pre-next form, treat it as an AND tree according to the pre-next.
Exactly. So that's why the quantifier elimination is available from a cylindrical algebraic
Thanks.
decomposition. But I agree with you that if you're only interested in exists problem, you don't need the structure of the tree. You just need to browse what is possible. You just want one path.
And that's why you say that the unset problems you don't see. The analogy I was making is you started out with Farkas lemma and simplex, which is not a quantifiable relation.
No. But I didn't mention, but it was written on the slide that this scales up the usual way. So the simplex explains how to eliminate a single exists, and then you basically use that to eliminate any quantifier by propagating negations and so on, which is not quite possible here. Okay. Because here I have nonlinearity, and it's a problem. Okay. So what about the existential problem, which might be simpler? So there is a notion of certificate. Well, I will really rush. There's a famous theorem called the Stangl Theorem, saying that you can have an algebraic identity that certifies that a certain nonlinear existential problem has no solution. But the problem is that it's not really easy to compute these certificates. It can be as hard as computing a cylindrical algebraic decomposition in full. So, but we hope to come up with more efficient heuristics.
Can you go back?
Sure.
Such that, okay, so P plus Q plus R squared is 0.
Yeah, so there are various ways of stating this. You can also put a -1 here and have strict positivity conditions instead of disqualities here. Okay. So I agree with you that there are more efficient methods for complete decision of the existential fragment, and this is often achieved by the so-called critical points method. So you have a function that has a local extremum on each component, and so you transform your problem into an optimization problem, and you find the local extremum, and then you get 1 point per component. Or there are many heuristics, like based on Grobner bases, computation of sum of squares, relaxations. Well, there's a broad literature on that kind of heuristics. So I don't have time to comment, but this has been a promising way of computing certificate and was initiated by the software developed by Pablo Parello on semi-positive programming. Well, my current investigations are to compute the exact counterpart of that kind of method. This can be done using so-called Bernstein bases. Maybe you can remember that this was an ingredient of the CAD algorithm. And also some people are working on exact positivity certificate using a posteriori correction of the answer given by Parello's software. So this will be my conclusion. So I hope to have convinced you that certificate producing decision procedure is something of interest, at least for us coming from formal proof assistant verification. So the point is that it requires to adapt decision procedures. Sometimes it's easy. In the case of linear arithmetic, for instance, it was not a big effort. But for theories like nonlinear real arithmetic, where even decision procedure is not really a well-understood topic, it's a challenge. So what is really striking in that field is that there seems to be little communication between communities from computer algebra and the people that are interested in nonlinear decisions, just like people from the hybrid system and control. So there are, of course, exceptions and other exceptions than the one I mentioned here. But it's not clearly known from computer algebra people that some computer scientists are interested in the results, and also the converse. So I will finish by saying that I'm currently implementing a prototype for basically experimenting nonlinear certificates. And this would include cylindrical algebraic decomposition, and that's almost done. Methods for complete methods for existential problems, like these critical methods I mentioned, and also exact positivity certificate based on sub-ingredients of cylindrical algebraic decomposition. Thank you.
Thank you. So, if a tool generates a cylindric algebraic decomposition,
Yes.
that's different from the Stangl
Stangl certificates, yeah.
Right?
Yeah.
But a CAD but wouldn't a CAD also be a
Oh, yeah.
kind of certificate?
Yeah, but if you have this result, then you don't need anything else. You have the complete information on everything
Right,
you would
but
like to know.
it could be false. I can give you a cylindrical algebraic decomposition, which is not
Which is not.
a real decomposition.
But from this decomposition of the initial problem you're interested in, it's not necessarily easy to compute the algebraic Stangl certificate.
Not
If it's false.
But could you use the CAD as a certificate
Oh, yes, sure.
on its own?
Sure.
Or check?
Sure. Yeah.
But you prefer this Stangl for the existential case?
No, for the existential case, so my hope is that these critical methods will be okay. So that's Grobner basis computations, which are easy to certify.
There's another.
Well, let's see. I guess ideally, I suppose I'd like to understand the CAD a little better. You're talking about the uniformity of the fibers, how each fiber has sort of the same pattern of solutions. So you do recursively decompose the fibers, but if you decompose sort of one of them, you've got them all.
Yeah. So if I take this problem in 2 dimensions, like let's say it's a sphere, so I project it, and I have a family in one variable, and these are the 2 roots, okay? So I have now these 5 cells. So I take a point here, it's Z, and this is my polynomial in 2 variables. And I study this fiber, which means I study P evaluated at Z and with variable Y. And this is a 1 variable polynomial with algebraic coefficients. Yes, I agree, but it's still a 1 variable problem. And so I look at it like this way, and this is a 1 variable problem, and I have 2 roots here, and that's what I use. So I have to know how to solve 1 variable problems, even if I have algebraic coefficients.
And what do you use for that?
So I have implemented so you don't need full algebraic number arithmetic. You only want to know the sign of the results of an algebraic operation on algebraic numbers. So I use, standard algorithms and naive interval arithmetic.
Right on. And then you were sort of complaining that the decomposition was too big, that it created lots of little regions.
Sure. Yeah.
I guess I could say, do you see any hope for doing better in that?
I guess that using elimination-based algorithm, you cannot really avoid this combinatoric exposure. But maybe there are other methods that are not recursive in the number of variables that might be more clever at figuring out that there are a lower level, a smaller number of cells. I don't know.
So it seems like since the quantifiers are picking out exactly those variables, that you sort of have to project and partition right along them. Right. So
I don't know. There is no proven lower bound. So for this problem, so it's known that an elimination algorithm has this complexity, and that's the best we can do.
So we don't know a lower bound for the real phenomenon, even the existential case.
I upped my knowledge.
So you can't judge. If you could change variables to just the radius of parts, then
sure.
For your sphere.
Sure.
But if your quantifiers are along x, y, and z, then
I don't know.
So I think one should be happy that this cat exists at all. I think it's awesome.
That's the optimist way of looking at it. Thank you again.